Bismillahirrahmanirrahim. Assalamu alaikum. In this lecture, we'll be discussing once again a half-wave rectifier circuit. But contrary to the last lecture, we'll have a different type of load this time. In the previous lecture, we had considered a half-wave rectifier circuit with a resistive load. In this case, we'll consider a half-wave rectifier circuit with RL type of load, or which is commonly referred to as resistive inductive load, or simply the inductive load as well, because we know that any inductance will have some internal resistance as well, even if it doesn't have any external resistance. Basically, this type of load is more practical in certain industrial applications where we have different types of motors and other machines serving as load to various type of sources. Okay, so the circuit that we'll have I will have in AC source. Okay, just like the previous case, we'll have a diode, and then we'll have inductance and a resistance in series to that one. Okay, need to have different labels. Since we are considering like inductance in series with the resistance, okay, so we'll consider the collective voltage across the inductor as well as the resistor as the output voltage. Okay, just like before, we'll have this equations because we are considering a sinusoidal voltage from the input source. Okay, that is what we will have. Okay, so this is the circuit that we'll be having in this particular case. Let us consider the case that we will have a sinusoidal voltage as an input. Okay, so if you want to draw the waveform for the source voltage, this is what we will have, the peak values of Vm. Okay, so this waveform basically represents the source voltage. So either we can label it over here, okay, as Vs, as we'll have it in this particular case. Okay, okay, so just before like omega t equal to 0, or in one of the textbook it has been labeled as t only. As I mentioned, it's up to like the individual as per the ease of understanding, the way we can understand it easily. Okay, but most of the books use this convention of omega t and label it as like in terms of its angular values, while some of the book also use some other notations as well. Okay, so prior to t equal to 0, as we know that the source voltage will be negative, and that negative voltage will cause this diode to be reverse biased. So that will mean that effectively this point is behaving as an open circuit, and there will be no flow of current through this circuit. So that is the one state of this circuit, that is the operation in this circuit prior to t equal to 0. If you want to label a certain current through this circuit, so that will mean that prior to t equal to 0, the value of current through this circuit is equal to 0. So at time t equal to 0, if we are considering an ideal diode, so we can say that like the diode which is connected between these 2 points will be replaced by effectively a short circuit, okay, because ideal diode will have 0 voltage drop across its terminals, okay. So at that time, now we need to consider the different waveforms, for example output voltage and others, that how they look like, okay, during that particular interval. We can also write the governing equation during that time period when we have like at t is equal to 0, or even we can say when t is greater than 0. During this interval, what will be the governing equation of this circuit, okay. So we can write, we can apply KVL to this circuit. We know the current I has now started to flow through this circuit. We'll have this equation. This is the source voltage that is like providing the current, while the rest of the quantities are resulting in a voltage drop across them, okay. So we'll have VR and VL, because we are considering the diode to be behaving as a short circuit, so we ignore any of the voltage that is being dropped across the diode, that is equal to 0, okay. We can substitute the values. So we'll have this differential equation that will be governing the current flow and the voltage drops across these various elements in this circuit. Okay, now here is something we need to understand at this point, because if we have a clear idea of this one, so it will help us like understand the whole theory of operation of this circuit and the subsequent circuits as well, in which we'll be having inductive loads or load of similar nature. That previously, as I had mentioned, that we'll have like a current that will be completely in phase with this voltage waveform, okay. So that is not going to be the case here due to this inductive load, okay, because the inductor has this basic property that it does not allow an instantaneous change in the value of current, okay. So current cannot instantaneously rise through an inductor. In the same way, current cannot instantaneously like fall to 0 through an inductor as well, okay. It needs some time to like rise to a particular maximum value, and then it also needs some time to go back to 0, okay. So it will be slightly different in this case. What is that difference, okay? But there is another thing that we have labeled a different voltage. We have given it the name of V0, okay. That is basically the total voltage across the sum of these two components, that is the resistance and inductance, okay. So the total voltage across the sum of these two components, that is the load, that is resistance and inductance, that will remain the same during this time, okay. So if let us say that if I want to have a plot for the value of total voltage across the resistance as well as inductance during this time interval from 0 to pi, okay, so that will remain the same, because effectively whatever voltage is being provided by this source, all of that is available across these 2 points. Now what is happening individually with resistor and inductor, we'll see that in a while, okay. But overall the sum of the voltage across the 2 components will be the same as being provided by the source, okay. Now let us see what happens individually with resistance and inductor. Previously, as I had mentioned, that the current through the resistive load, previously we had a resistive load. So if we just quickly recall that previously the current was of this shape, okay. It was, since we have this equation so the current was slightly lesser than the voltage due to this resistance, but it was not it was having the same waveform as the voltage. Now here it is not the case. Okay, the current will not be of this shape. Of which shape it will be, let us investigate that in a bit more detail. Okay, now since the current cannot instantaneously rise to a maximum value, and it will gradually rise to a maximum value, so it will not follow this path. Okay, it will like very slowly rise to another maximum value. Okay, so what happens with the voltage, because we have already mentioned that the voltage at this point is going to be available across these 2 points. So what will happen that during the initial time when the current is exactly 0 or is having a very low value, so when the current is having that value equal to 0 or it will be having a very low value. Okay, I'll plot those waveforms for current and voltage over here. For the resistive, current will be of course the same through the whole loop, resistance and as well as inductance, but the voltage across the two will be different. Okay, so the current will be gradually rising. Okay, and the same will be the case with the voltage, that it will also be slowly rising. So this is the current waveform and this is the voltage waveform, slightly higher than that. Okay, or let me draw these waveforms with a different color across this point over here. Okay, let us say that this is the current through this circuit. Okay, and this is the resistive voltage. Okay, this green color basically represents the voltage and this waveform represents the current through this circuit. Okay, so what happens, what about the voltage? Because we have already mentioned that this red color represents the output voltage, and that is basically the voltage across the sum of these two components, that is the resistance as well as the inductance. Okay, so basically what happens that initially when the current is gradually rising, so all the voltage that is written or being represented by V naught over here, all that voltage appears across the inductor terminals. Okay, so at this point this voltage over here is maximum, and that is basically as long as we have this VR equal to 0, so Vs is basically equal to VL during this interval. But as gradually the inductor starts to you can say build that energy or starts to store that energy. Okay, so during this time that voltage across the inductor is gradually rising and the voltage across the resistance is also rising, but the net sum of the two voltages is always equal to the source voltage. We can also rewrite this equation, this one in this form as well. Okay, so as we can see over here, this will also tell us the true story or will help us understand the actual story with a bit more ease, because Vs is gradually rising up till a certain point. Okay, you can see over here that there is a certain point up till which Vs is rising. It goes to a maximum value and then it starts to fall to its minimum value, that is equal to 0. So we can see over here, as long as we are having this Vs rising to a particular value, okay, it is gradually increasing. So during that same interval, what is happening that the current is also gradually rising, so the voltage across this load or this resistance is also rising. Okay, so what happens is that during this time interval the inductor is also energizing and the voltage across the inductor is also gradually rising. So there is a brief time during which all of these voltages are having waveforms or slopes of something like this. Okay, so during this time, the resistive part of this load also starts to have a higher voltage drop across itself, and gradually the voltage drop across the inductor starts to reduce, and the voltage across the resistive part of this circuit starts to increase. Okay, so there is a time that when the voltage drop across the inductor reaches its maximum value, okay, and then it starts to fall. Keep in mind that the sum of this is the voltage across the inductor. Okay, so you have to keep this in mind, that the total sum of the voltage across the resistive and the inductive part of the loads is also always going to be equal to the source voltage. That is this original blue color waveform, or we can also say that is going to be equal to this part of or the red color, which is the output voltage. Okay, so after a certain time that this starts to fall to a low value. And this is the time that this keeps on increasing up till this time, for example. And the current also keeps on following the same pattern. Okay, this is the point basically over this curve, in which we can see that this is the point at which VR and you can say the source voltage, this is the curve for the source voltage, both of them become equal, so that results in the inductor voltage becoming equal to 0. This is how it has been represented over here with the help of this this point over here, that this is the point of intersection of the voltage across the resistive part of the load, and this is the same point which is representing the voltage across the inductive part of the load, that that becomes equal to the source voltage. Okay, so at that point the inductive voltage becomes equal to 0. So now you can imagine what is going to happen beyond this point. Okay, that this is the point for the current at which the current has already reached its peak value. Okay, it has reached its peak value, and after this the current starts to gradually reduce. Okay, and you can clearly see that the current is lagging the voltage waveform, and this is what happens in the case of inductive load, and the extent of lag depends on the value of the inductance in itself. Okay, so after this point the current will gradually start to fall. Okay, and as I have mentioned in the beginning, that the resistive part of the load and the current will have, because they will be in phase with each other. Okay, so this will be following exactly the same shape, that beyond this point it also starts to gradually fall down. But what happens with the inductive voltage, and that is interesting, and that is we need to take a note of that one, that because I have mentioned that the net sum of the inductive voltage and the resistive part of the load, the voltage across the resistive part and the inductive part is going to be equal to the source voltage. Now here in this case we can see that VR is greater than Vs. Okay, so for it to become equal to Vs, the net sum of these two, the inductor voltage, has to be negative. Okay, and I'll explain the mathematical reason beyond that as well, but now let us focus on this part for a while. Okay, that this will keep on being negative for a while, because as long as this voltage is decreasing. Okay, although that this is following this falling slope, but since we are having inductor over here, so it will take some time, because the current is gradually reducing to that 0 value. It cannot instantly become equal to 0. Okay, so by the time this one becomes equal to 0, so the voltage across the resistance is also following the same pattern. This also becomes equal to 0. Okay, and this is the time which is required for this inductor during this voltage or this energy which has been acquired by the inductor, that is completely released. Okay, so this is how this waveform of this shape looks like, or this is how it takes it. So this is a more according to the scale representation of the same waveform that we have just seen, of that we have just considered. We can see over here this is Vs or Vd. We can see this is the original source voltage drawn over here. So up till this point Vd is also the same. There is one more thing that I would just like to explain beyond this point in that same figure. That point is that unlike the previous case in which we had the resistive load only, okay, and as soon as the output voltage used to become the source voltage used to become a negative in polarity, the diode would reverse bias, okay, and the output voltage becomes 0. Now here you can see that even beyond the point when the input voltage, the source voltage, which has been represented by this blue color, has become negative beyond this point labeled by pi, phase angle pi, okay, still we can see that the current that is flowing through this circuit remains positive, okay. Still, that is because the inductor current, okay, which was there, does not allow the current to instantaneously become equal to 0. The inductor had acquired some energy, it had gained some energy, and it needs some time for that energy to be released, okay. And at this point, although that the current has started to drop because the source voltage is having a lesser value with every passing instant, okay, but it needs some time to drop to a minimum value of 0. So what it means that that we will have output voltage, although that because of this equation that we'll have this V voltage across the load, okay. We can say it V0, that is the sum of VR and VL, okay. So beyond this point we can see that up till this point that since we are having this output voltage, up till this point it is quite straightforward that both VR and VL positive, so V0 will also be positive. After this point, during this brief interval, okay, during this time, okay, we can see that the value across the resistance, this represented by this green color VR, is much higher than the negative voltage that is now building across the inductor. So this one is still positive, okay. But after this point we can see that gradually the effect of this negative voltage there across the inductor, that this is the point, as you can see over here, this figure is not exactly according to scale, we'll see that figure in the book, that this is the point at which VR and VL are exactly equal to each other. So that results in the output voltage becoming 0. And after this point we can see that the VL is more negative as compared to the positive value of R, okay. So this value is smaller than this negative value, that results in the output voltage becoming negative. And beyond this point, that point is still valid, that Vs is equal to the sum of the resistive part of the load plus the inductive part of the load, or V0. So it follows the input voltage waveform, okay, but it continues like that. So as soon as at this point the current that is flowing through this circuit becomes equal to 0, so immediately we'll have the diode turning into reverse bias mode, okay. And now we'll have no more flow of current, and that will mean that we'll have no more voltage across these components, and all the voltage will now appear across the diode. So now let us see more clear waveforms from the book. Okay, so let us see this representation from this book first, and then we'll see the other one, okay. As we can see over here that this is the waveform across the from the source, okay. Then as I had mentioned that there will be a gradual rise in the voltage across the resistance because the current is gradually rising. So you can see over here that during this initial period all the voltage that is being applied by the source is appearing across this inductive load, okay. You can see VL completely represents the input voltage. After this point you can see gradually the current starts to rise, so the voltage across the resistive part of the load also starts to rise, okay. But the sum of the voltage across the resistive part and the inductive part will always be equal to the total voltage across the load, and that is in fact equal to the total voltage that is being provided by the source during this positive half cycle, okay. So the inductor voltage reaches its maximum value, so as the inductor voltage keeps on rising and attains a particular value, and we can see that the voltage across the resistor has also risen to a maximum value. So beyond this point, the voltage across the resistor still keeps on rising, while the voltage across the inductor starts to fall, because now what has happened that the current has gradually attained its maximum value, and that results in the value of voltage across the inductor becoming equal to 0. We can also explain this with the help of this relationship, that we have this governing equation for the inductor voltage. Okay, this is the representation of this one. So as long as we can see that as long as the current is having a positive slope, okay, the current is rising, so the voltage across the inductor will be positive. Okay, and as soon as the current starts to fall, it has a decreasing slope, so the voltage across the inductor will become negative. So we can see over here that up till this point, okay, this is the time duration, this interval in which the current is rising. Okay, so the voltage across the inductor during this whole interval is positive. This is the time duration in which the current has like a negative slope, it is falling, so the voltage across the inductor during this whole time duration is equal to 0. And this is the point at which you can say that for a brief amount of time the voltage the current across the current through the inductor is constant. So for that we know that the derivative of this term will be equal to 0, and that is the reason that the voltage across the inductor at this moment of time will be equal to 0. Okay, so this point has been referred to as like alpha in some books. Okay, and this has been referred to as beta in some of the books, while in one of the books that is of Nat Mohan, that will be referring to some discussion now as well, these points has been labeled as T1, T2 and T3. Okay, so it does not make a lot of difference, it is for the understanding purposes. Okay, so you can see the waveforms again more clearly over here. Okay, the same waveforms have been represented in a slightly different way in the Daniel Hart's book, but the main theme is same. But in this case, some of the students may find this representation a bit easier to understand. Okay, so this is the source voltage we can see over here. Okay, represented by Vs, and we can see that V0 is exactly following the source voltage up till this point beta. Vr, as I mentioned, that will gradually rise from 0, as we can see that the current and the resistive part of the voltage will have be in phase. Okay, while the voltage max initially attains a maximum value. Okay, and then it with the drop in the value of current, it becomes negative. Okay, this is the waveform across the you can say diode part of the circuit, that is during the negative half cycle, that it will have from you can say the voltage appearing across this will be from beta to 2 pi. Okay, a bit of mathematics. Okay, that the voltage across the inductor part of the circuit is represented by this equation. If we rearrange this equation slightly, so we can have so if we integrate both sides of these equations from the start up till the end point of conduction, that was T3 if you remember for this whole cycle. Okay, this was for the output voltage, this was referred to as T3, this was T2, this was T1, at which the inductor voltage becomes negative, first becomes 0 and then becomes negative beyond this point. Okay, so if we integrate both sides of this equation for this whole conduction period, let me draw the inductor voltage waveform for as well. This is the output voltage. Okay, if I draw the inductor voltage waveform for this one, okay, okay, so the current that is flowing through this circuit during this time duration, that is from time t is equal to 0 to time t is equal to t3. Okay, basically if we remember the waveform of current, that was something like this for this time interval. So we can see that at time t is equal to 0 at this point, and at time t is equal to t3 at this point, the value of the current waveform, if we evaluate this integral, that was in fact equal to 0. Okay, so with the help of this one we can equate this equation, this side of the equation, to 0 as well, and that will result in this function. Okay, now this takes us to one interesting principle that we have already discussed quite in detail for the case of switched mode power converters. If you can quickly recall that one. Okay, but before going to that one, basically what it does, that it represents the inductor voltage for this whole interval, that is from 0 till this point t3. Okay, but here we can see that the inductor voltage is having both positive and negative values during this time interval. So what we can do, that we can have a more clear interpretation of this one, that is we can represent it with the help of these two sub-intervals. Okay, that is from 0 to t1 and then from t1 onwards to t3, and that is in fact equal to 0. Okay, and this is basically that volt seconds, okay, that we have had quite a detailed discussion upon in the previous lectures related to DC-DC converters, and these principles stand true over here as well. Okay, that the total area, in terms of area, we can specify it like this one. Okay, if we label this one as area A and we label this one as area B, from 0 to T1 and then to T1 to T3. So what we used to see in that principle, that the total area or the average value of the inductor voltage over the entire cycle is always going to be equal to 0, and that can be established if we just have a closer look at this one, and we say that we'll have like equal amount of area covered by the inductor during these two sub-intervals, and that stands true as well, because we know that whatever energy has been gained by the inductor, that would be lost by the inductor. Like the inductor is gaining energy when the current is on the rise. Okay, the voltage across this is positive for this interval when the current is rising, and then when the current starts to flow, so the voltage across the inductor is negative, and it like sort of loses the energy. Like, so we used to have that discussion in the previous cases. Okay, that what we will be having the performance analysis parameters, like we had a purely resistive load in the previous discussion. Now we have a resistive inductive load over here. We remember that what waveform we used to have in case of purely resistive load, and what waveform now we have in the case of resistive inductive load. In the case of purely resistive load, you remember that we used to have this type of waveform from 0 to pi. Now here in the case of resistive inductive load, we are having like something like this. Okay, there is some negative part of the voltage over here. So it is clear that if you compute the average value or the DC value of the voltage for a resistive inductive load for an RL type of load, okay, so you'll have an average value or a DC value which will be lesser than the case what we will have in the case of a purely resistive load. Okay, and if you want to evaluate the average values, for previously we used to have that function in which of course the total time period will still remain 2 pi, but previously we used to have the value from 0 to pi. But now here we can see that the voltage keeps on like conducting till so here now in this case, in the case of RL type of load, we'll have this value equal to beta. So then beta actually in practical depends on the value of the inductance, and that for how long this keeps on conducting. So this can then vary from circuit to circuit or application to application.